Okay, so the method we use to plot vectors on the complex plane is what we call like a rectangular approach, where you have two perpendicular components, one in the x direction, which is real, one in the y direction, which is imaginary. But there's another way we can do this. We pretty much, when we're using a plane, we can come up with schemes that use any two parameters. So here's a different way of looking at that, using what we call the polar form or polar coordinates. Suppose I have an imaginary number out here with some, this number represents some x plus y j value, y times j. So this is the imaginary component, and this is the real component. So I can put this in point pair form, x, y, for this point. And let's draw a vector to it. So draw a vector to this. This is 0. So again, this goes out. This goes out 1, 2, out to infinity. And this goes out. Same deal. Except along the vertical, these are imaginary. So 1j, 2j, 3j, so on and so forth. Well, this point up here has an x value associated with it of 3, right? So here, x equals 3, and y equals 4. Well, as we look at this, we see that there is an angle this makes with the x-axis, or the real axis. We can call this angle theta. And the length of this vector we call the magnitude of the vector, or r. So r equals the magnitude of the vector. The absolute value of r is the magnitude of the vector, I guess. And I'm thinking of this r as a scalar length. So the actual length of this r we can find as r squared, because now we've made ourselves a right triangle here, right? And so r squared equals whatever our x is, x squared value, plus y squared with our Pythagorean theorem. So r equals the square root of x squared plus y squared. So here in this situation, r equals the square root of 3 squared plus 4 squared equals the square root of 25. So r equals 5. So r has a length of 5 now. And we can also think of this as x. If we knew what r was and we didn't know what x was, we could think of this as x equals, well, look at this. This is adjacent over hypotenuse r. So x over r equals the cosine of theta. So if I multiply both sides by the equation by r, we end up with x equals r cosine theta. And y, the vertical distance of this triangle, is the opposite over r. So y will end up being r sine of theta. And if that's the case, we know that tangent of theta equals y over x, or opposite over adjacent. So we can use this idea if we know what x and y are to figure out what the angle is, right? We can take the arctangent or the inverse tangent of this y over x, and that's going to give us theta. So now we can express our vector instead of in terms of x plus yi. We can describe it in terms of r and theta. So we can describe our vector with this polar notation. With two different values with r and theta. So r equals 5 and theta equals the inverse tangent. I guess we didn't calculate it up there, but the inverse tangent of 4/3. If you throw that in your calculator, you end up with theta equals 53.1 degrees. So we could write it like this: r equals 5 at 53.1 degrees. Shorthand we can use, you might see this appear somewhere with a shorthand, where we would write it just as r angle theta, or in our case it would be 5 angle 53.1 degrees. Sometimes it's written like this: 5 angle with the line long 53.1 degrees. So in summary, in the previous section we had x plus y j as our complex number, but now we know that x is r cosine theta plus r sine of theta as our j component. We can pull the r out. R cosine theta plus sine theta, our quantity, sine theta j. And if we put actual numbers in here, we would have 5 cosine of, say, 53.1 plus sine of 53.1 j. And we could just simply write that as 5 angle 53.1 degrees. So, example, say we have three cosine of 120 degrees plus j, I'm putting it in front now, 120 sine 120 degrees. We could also write this. We could write this one as 3 120 degrees. And we could easily plot that if I wanted to. One, two, three. 1, 2, 3. So this is 90 degrees here. And then 120 degrees is about right here. And then a distance of 3. This would come up here to distance of 3. Something like 120 degrees, something like that. Let's change the color of this. Make it green. So this angle is 120 degrees, and the magnitude here is 3. So we're not really using these rectangular coordinates to plot this. We're using, instead of an x value and a y value to plot this point is represented by a magnitude and an angle. So let's do this example. So if we have the impedance Z of magnitude 35 with an angle of minus 32.4, let's plot this on a Cartesian complex plane. So here's our complex plane. We'll continue to call that J, I guess. So Z is going to equal R times the cosine of theta plus I sine of theta, or let's make this J. So this equals 3560 times the cosine of minus 32.4 plus J sine of minus 32.4 degrees. So this means that our x value is 3560 cosine of minus 32.4, and the y value is 3560 times the sine of minus 32.4. Well, this in your calculator equals 3010, and this ends up equaling minus 1910. So 1,000, 2,000, 3,000, 4,000. So this is about there, and then let's go 1,000, 2,000. So this is somewhere around 3,000. It's right here. So this is your point 3010 minus 1910. And we can draw certainly a vector to that. Of course, this is 0 here. And that's it.